First, introduction. So it started from the mid-19th century. The physicists, whatever they observed, the absorption and emission radiation by heated object, then it is called the thermal radiation, and they tried to figure out that what is the thermal radiation. Then this thermal radiation, it is a well-known fact that it consists of electromagnetic waves of various frequencies or wavelength, and it is based on the number of modern concepts. First active study of the thermal radiation's laws occurred in the 1950s. And this theory of electromagnetic waves and the emission of such waves by accelerating charged particles was developed in the early 1870s by the Maxwell, which was experimentally confirmed by the Heinrich Hertz. And the Maxwell suggested that when the electrically charged particles moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. This is observed by James Maxwell in the year 1870. So these both electrical and magnetic fields transmitted in the forms of waves, which is called the electromagnetic waves or electromagnetic radiation. So we know the light. Light is nothing but it is a form of radiation, and it is known from the early days, and it is from the very long time it is known in the ancient times. So we can visualize this nature. We can find out that this is the magnetic field component, this is the electric field component, and this is the direction of propagation. So here you can see that when you go, then this one will come. Suppose you consider the z-axis. From z-axis it is down, and then it will come to the y-axis. So it is perpendicular, and again the direction of the propagation is the x-axis. So with this x-axis, both electric field component, which is along the z-axis, and magnetic field component, which is the y-axis, both are perpendicular to the direction of the propagation. So here we are mentioning that the oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other. That means this direction for electric components, field components, and y direction is for the magnetic field components. So the z and y axis is perpendicular to each other. And also you can see the direction of propagation is the x-axis, and both are perpendicular with both the z-axis, which is for the electric field components, and y-axis, which is the magnetic field components. Second properties, unlike the sound waves always need some medium, but for this case you do not need, for electromagnetic waves do not need any medium and can move in vacuum. And that is the reason why the electromagnetic wave, like light, is coming from sun, moving through so much vacuum place is there, but till now it is reaching to us. So it is now well established that these electromagnetic waves, many types of electromagnetic radiation, electromagnetic waves and electromagnetic radiation, both are synonymous, and different types of magnetic radiations, they are differed from one another in respect of wavelength or frequency. And here you can see that we'll go for details, that different wavelength, different portion magnetic rays here, gamma rays, X-rays, UV, IR, microwave, FM radio, we know that is very famous, and others long radio waves are there. So they are the different types of the electromagnetic radiation. So their wavelength differs from each type of electromagnetic radiations, and they all constitute, and it is called the electromagnetic spectrum. This whole thing is the electromagnetic spectrum. So different kinds of units also we have to use for this to represent the electromagnetic radiation. So here you can see the different unit is there. If wavelength, it is the lambda. For the frequency, for the SI unit of frequency, also hertz, Hz per second inverse. After the hertz has done some experimental determination for this electromagnetic radiation. And what is the hertz? It is defined as the number of the waves that pass a given point of in 1 second. Per 1 second, how many number of waves is passed a given point. And wavelength should have the unit of the length, generally meter. And as you know that the SI unit of length is meter. And since the electromagnetic radiation consists of different kinds of waves of smaller wavelengths, smaller units also used. And this figure shows that various types of electromagnetic radiations which differ from the one another. You can see that this is the wavelength. It is in respect of nanometer in m. So it is the smaller unit of the meter. Now in vacuum, all types of electromagnetic radiation, regardless of the wavelength, travel at the same speed. We know the speed of the light. It is the 3.0 multiplied by 10 to the power minus 8 meter per second, or precisely it is the 2.997925 multiplied by 10 to the power 8 meter per second. And this speed of the light is symbolized by the small c, and the frequency and the wavelength and velocity, if you consider, then you will find one equation which is given is the below. And the other commonly used quantity for this spectroscopy is the wave number, and the wave number is defined as the number of wavelength per unit length. So its unit is meter to the power minus 1. This is the SI unit, and common unit is cm to the power minus 1. That means centimeter to the power minus 1. It is not the SI unit. Now we'll check the different regions of the spectrum. So if you see the spectrum, and above one scale is there. So we start from right to left. And then if you see the radio frequency region, it is the 10 to the power 6 hertz. So radio frequency region, this is the 10 to the power 6 hertz. And it is used for the broadcasting. We know that FM radio is there. And the microwave region, we know we have the microwave oven. So it's 10 to the power 10 hertz. So this is the microwave region, is that region. And after the left side again, it is the IR region. IR actually it is used for the heating, infrared. So this is the 10 to the power 13. 10 to the power 13 region. In between you see that 10 to the 12 to the 14. So it is in between 10 to the 13. After IR, next is the visible region. You can see that this whole band from 400 nanometer to the 750 nanometer, whole range is the visible spectrum, and it is the visible region which where we can find the visible light, and this small portion around the 10 to the power minus 15 hertz. You can see here 10 to the power 15, and after that the UV region is the 10 to the power 16 hertz. That means this portion is the 10 to the power 16 hertz. Special instruments are required to detect the non-visible radiation. That means whatever left side radiation is there, then we have to check it with the special instrument. And now the problem is there. So you can problem the Bipti Bharati radio station of All India Radio, Delhi, broadcast on a frequency of the 1.368 kilohertz. Main unit is hertz, and if it is multiplied by the 1000, then it's the kilohertz. Calculate the wavelength of the electromagnetic radiation emitted by the transmitter. Which part of the electromagnetic spectrum does it belong to? So we know this equation, we already discussed in the previous class. So with this, now lambda is c is the light speed, and this is the frequency. So frequency here 1.368 kilohertz. That means 1368 and then again we calculate this, then ultimately whatever the wavelength is there, then 219.3 meter, and this is the characteristic of the radio wavelength. So today you understand that what is the electromagnetic radiation and what is the different unit and what is the different region of the spectrum. And spectrum consists of a range of the electromagnetic radiation, and there is some problem how to calculate from the equation the wavelength if we have given the frequency.